Okay, finally, we will be talking about number 3 from this set of review problems for the semester 1 AP Physics final. And in number 3, it's a projectile motion problem. We're just using our understanding of kinematic equations and motion in the x direction and the y direction. So in number 3, a ball is projected upward at an angle of 65 degrees to the ground with a velocity of 13 meters per second. So what we're given is the magnitude and direction of the initial velocity. And this is a two-dimensional problem, so we have to break down that velocity using what's been given into x and y components. And we've already got an x and y coordinate system set up. And part A asks, what are the horizontal and vertical components of that velocity? So we are given that there's a 65-degree angle, launch angle, and it's 13 meters per second. So what we're trying to solve for is this y component and x component of velocity. What are those? If this y component, we'll start with the x component. This x component is adjacent to the angle that's been given. And I may want to use cosine. Cosine of 65 is going to be adjacent over hypotenuse. And hopefully this comes out to be something where we're just left with one thing we don't know, and the thing we don't know is what we're looking for. Cosine of 65 adjacent is the thing that we're looking for, and the hypotenuse is going to be what's given. And I'll write it out as just a variable. It's just going to be v. So rearranging this, it's going to be v cosine 65 is equal to vx, which is what we're looking for. V, of course, is 13, so the x component of velocity is just 13 times the cosine of 65. And this equals 5.49. And I'm going to do the same thing to find out this y component, except I'm going to use sine, because when I set up the sine for this given angle, I'm going to use the opposite, which is what I'm looking for, divided by the hypotenuse, which is the magnitude of this velocity vector. So solving for Vy, I get V sine 65, and that's 13 times the sine of 65. And that equals 11.7. So at this point, I may want to do a little gut check, just to check that these numbers make sense. Now I can go ahead and plug them into the Pythagorean theorem and just kind of, or do some mental math to see that those make sense. This 65, if this is 65, then this must be 25. Yeah, 25. And so the side that's opposite of 25 degrees should be smaller, shorter compared to the side that's opposite of the 65-degree angle. Vy I got 11, and Vx across from this 25-degree angle I got 5.49. Okay, so that kind of makes sense. This angle is like half of this angle, so I can imagine that the side length is going to be about half of the side length for the one across from 65 degrees. So that's enough for me to kind of be okay with moving on with these numbers. Part B, assuming there's no drag force, there's no forces acting in the x direction, how long is the ball in the air? So one way we may want to do this is to declare that based on what was given, by the time the ball takes off and lands, the change in its y position will be 0. It's going to land right back where it started. And that's convenient in a problem like this because there's no mention of it launching from any height that's above the ground or below the ground. So its change in position in the y direction is just going to be 0. What else do we know about the y direction? We know that there's an acceleration due to gravity, and that's the only force acting on a ball as it's going through the air. There's no applied force, there's no friction force due to air that was explicitly mentioned in the problem. There's no tension force, there's no normal force because there's no surface. So the acceleration in the y direction is strictly due to the force of gravity, and anything that's accelerating due to gravity is negative 9.8. What else do I know? Well, I want to know the time, so I'm going to make a note of that. And I know its initial velocity. Now this is where we really want to be careful, because a lot of us are tempted to use this 13, this vector, this velocity vector that we were given. But this is a two-dimensional problem, and if we're going to talk about displacement in the y direction, acceleration in the y direction, then in order to do so meaningfully, we need to talk about velocity in the y direction. This x component velocity has no effect on the y component velocity, which is kind of creepy, but it's a two-dimensional problem, and whatever goes on in one direction isn't affected by what's going on in the perpendicular direction. So the initial velocity is not 13, but rather what we found in the first part, 11.7. Okay, so these are my knowns, and I think what I want to use then is this kinematic equation. And I could just plug in what I know. Oh, I'm going to just leave out the units for now just to simplify. So what I'm left with is a quadratic equation where my a is this 1/2 9.8, which simplifies to 4.9. My b is positive 11.7, and my c is 0. So I can, you have options of what you can do here. You can complete the square, you can use a quadratic formula. If you're brave, you can factor. I'm going to use a quadratic formula. Oops. Minus 4ac all over 2a. And this is going to be negative 11.7 plus or minus the square root of 11.7 squared minus 4, negative 4.9, and 0. And this is all over 2 times negative 4.9. So you'll notice that because this term is being multiplied by 0, we're just going to be left with the square root of 11.7 squared. And so I'm going to have two solutions for t. One of them, 11.7, negative 11.7 plus 11.7, all over 2 times negative 4.9, which is going to be 0 because these two balance. And my second solution, and well, let's think about this one. Well, of course, when the ball gets projected, the moment it launches, its height hasn't changed. That's the condition we set here. Yes, it's still accelerating due to gravity. The whole time it's accelerating due to gravity because it has mass. That's not going to change. And this was its initial velocity. So the moment it gets fired, there's no change in velocity. So this has to be true. The second answer is going to be what we're looking for. This is after it launches. And that's negative 11.7 minus 11.7 divided by 2, negative 4.9. This top number is 23.4. And at the bottom we have, well, that's negative, but we have a negative at the bottom too, and that's negative 9.8. And the amount of time it takes in the air to land is 2.38 seconds. And for our final answers, I want to check back, see how many sig figs were given, and it looks like everything was given to 2 sig figs. So my final answer may be 2.4. Okay, next part. How far does the ball travel horizontally? Well, so I'm looking for delta x, and I have to be careful anytime if I'm gonna use a kinematic equation, I have to make sure that I'm using initial velocity in the x direction, and we found that in the first part to be 5.49. Meters per second. What else do I know about the x direction? There's no acceleration. There's no drag force. There's no force acting on it in the x direction that would change its acceleration. And we can get that from Newton's second law. If there's the sum of the forces is equal to 0, then its acceleration is 0. We want the change in x. We know that the amount of time it took to land was 2.38 seconds. So maybe we can use that. It looks like we have all the same knowns as the last part, so maybe we can use the same equation. This is going to be 5.49 times 2.38, and acceleration is 0. So I'm not even going to bother putting that in, but that's 2.38 squared. This whole term goes away, so the change in the x direction is just that 5.49 times 2.38. And this should be a 3. And 13.1 meters. Okay, that seems reasonable for something that took off 13 meters per second. That's pretty fast. 13.1 meters, that's probably the length of the room, our classroom. And so that seems okay. I'm okay with that answer. I can sleep tonight. What's the ball's peak height? Several ways to do this. I'll show you one way, and I challenge you to come up with a different way. What part was that? D. So peak height, delta y. The final velocity in the y direction when it's at peak height for just a moment is 0. And we know its initial velocity in the y direction from the first part to be 11.7. I know acceleration in the y direction is negative 9.8. And so the equation that's going to help me out here, kinematic equation, right here. And again, I challenge you to come up with a different way to do this because there are multiple ways, including using information from previous parts. So final velocity is 0, 11.7 squared plus 2, negative 9.8, and then what we're trying to solve for. I wrote delta x here, but I really mean delta y. Okay, so moving this over, and then I'm going to move this over, so it's negative, and then divide by these two numbers to isolate delta y. And that equals 6.98 meters, and to 2 sig figs, that number will actually be 7.0 meters. So very quickly, I want to talk about part E. What forces are acting on the ball while it's in the air? It's only the force of gravity. There's nothing else interacting with the ball. And if we wanted to make this an isolated system, the objects would be Earth and the ball. Earth is applying a force to the ball, and that force is being balanced out by the ball's acceleration changing. That's Newton's third law for every action, equal and opposite reaction. I already mentioned, there's nothing else interacting with the ball.